All right, I'm recording. Shh, shh, shh. Here we go. So we're now moving on to exercise 17B. 17A technically is no longer on the course, but it is the theory that I wanted you to take out. Okay, so last session, I showed you how to do what we call first principles. So recap, first principles allows you to find the gradient of a tangent line at one point on a curve. Okay? This is your curve. So they will always give you a curve, and that curve could be any type of function. It could be cubic, exponential, logarithmic, circular function. In our case here, it's a quadratic. So on a curve, they want to know what is the gradient if I drew a tangent line at that particular point. What is the gradient of that line? That's essentially what you're looking for. I taught you first principles. This is a long, tedious way, but one of the things the reason why I wanted you to do the algebra to it, even though I know there's a shortcut to getting to this answer here, was the notation. You see, what we're doing over here is the skill next year, chapter 1, you are going to be dealing with function notation. So by practicing it in 17A, as tedious as it is, it's getting you more familiar with the question. So when you ask me, like, do I have to do it? I'm like, yes. The reason why I say yes is because I know as you're doing it, the elements of your layout is what builds your familiarity. Because next year, you're going to learn what we call composite functions. And most times, students struggle with it, not because of the theory, but because they don't know how to read function notation. Okay, so that's why you have to do 17A. Now, today's lesson, assuming that you somewhat got through 17A, 17B, I'm now going to teach you this shortcut to finding, going from this equation, I'm going to just change that, this equation all the way to that. So you can do that within a couple of steps by knowing one formula. And that only works for these particular type of functions. So we call them polynomials. Out of curiosity, anyone remember what polynomials mean again? Ollie. That is part of it. It's true. Lots of solutions. What else? It is a particular type of graph, which is special. It's to the power of. Okay, so as long as you have polynomials means that you have quadratics, cubics, quartics, quintics, and you follow that x to the power 1, x to the power 2, x to the power 3, those together under the umbrella term of polynomials. That's why when you did cubics, that chapter 6, was not called cubics, it was called polynomials. Because you did a bit of cubics and technically there was quartics in there too. But in general, this rule that I'm about to give you only works for a shortcut to doing all of this. Instead of doing all of this here, it's a shortcut for any curves that is considered a polynomial. Okay? So this is the rule that I want you to copy down. So this rule here says f of x, if you have a function, if the curve happens to be a polynomial, so this is a polynomial, right here, polynomial, then this is the rule to find the derivative. So the derivative, remember, it's the gradient, which we do f dash of x, that's the notation, is equal to, and the formula is n, so whatever the power is, n in front of x means times, x to the power, whatever that current power is, minus it by 1. That's the rule. Okay, so n could be, so you could have had x to the power 3, x to the power 4, x to the power 5. That's what this represents. The n value means you could have n to the power of anything. From here, the derivative, you can find it by whatever that power is, it's that power times x to the power of wherever it is minus 1. So if we're using this rule, so as you're copying down the rule, let's have a look at the example that was given. So the one we did before in exercise 17A, I did the whole derivative with first principles to finally get our answer, and I used the limit, talking about h approaching 0, and then you were able to figure out that the result was 2x plus 2. So let's use that rule for our function now. So our function, so I'm going to do the same thing as an example. F of x is apparently x squared plus 2x. Okay? What I can see here is they're both polynomials. So this is a polynomial. It's x to the power of 2. This one over here is a polynomial because it's x to the power of 1. So that means you can derive them or differentiate them or use the rule for each of those terms individually. So when we write the derivative, let's find the derivative. So f dash of x, you can get straight to the point by using the rule. So let's do it individually. X to the power of 2, what's n equal to in this particular term? What's n equal to? 2. N is 2. So according to my derivative rule, f dash should be 2 times x to the power of 2 minus 1. So if I write that down, 2 times x to the power of 2 minus 1. This should give me 2x to the power of 2 minus 1, which is just 1. So it's 2x to the power of 1. And then you do the same for the next term. What is my n term for the second term? We can say that n equals 1. So according to the rule, again, I'm going to highlight this point here. When you're differentiating, it has nothing to do with this 2, because that's not a polynomial. It's this that you're differentiating. So another way of thinking about it is you're adding on 2 times and you're differentiating x to the power of 1, because that's what the rule says. The rule says I'm only differentiating x to the power of whatever it is. So I'm differentiating x to the power of 1. And according to the rule, n is 1 times x to the power of 1 minus 1, right? So if I do that, this now gives me 2x plus 2 times 1 times x to the power of 0, but we know x to the power of 0 is 1. So we can write that as 1. But then 2 times 1 gives you a final answer of 2x plus 2, which is exactly the same as what we got down here. This is called the power rule. Okay, so I'm going to write here, this rule that you have here, this is called the power rule. You will find that after you learn this, you might forget the meaning of what you're actually doing, because as you learn more rules, you just kind of do it as you do. Most students in the state, on average, can differentiate. That's not the problem. The problem is they don't know what they're doing. They don't know what it means. So I'm going to keep reminding you that, remember, this is a shortcut from doing this. This is the first principles. It is the theory. It is the foundation of it all. You're simply saying, I want to find the gradient at one point, but I don't know how to do that. I'm choosing a second point, and I'm infinitely making the second point as close to the first point. So technically, when you find the gradient, it gives you the gradient of one line, or the gradient of one point. That's the theory. Instead of doing that, which is limits and it takes a long time to do, they found out through proof, and there's a proof at the end if you're interested in it. That means you need to know Pascal's triangle and binomial theorem for those who want to push themselves and look at the proof. You don't need to know the proof, but that's where it comes from. That proof stems from here, and then if you go down the proof, that's how they got to this formula here. Okay, so this only applies for polynomials because that proof was based on a polynomial. Okay?
Will we learn about Pascal's triangle?
You may in year 12, some schools will go through just so that you understand combinations. That's not really needed. It's usually found in appendices. So in your textbook, you got your chapters, you got your contents, and at the very end, around the glossary section, appendices have some extra theory. You'll find binomial theorem there if you want to look at it. You don't really need to. You can get by without it.
It's only for the binomial theorem and like combinations of
Correct. So most times they just teach you when it comes to binomial distribution, but they won't actually go through the whole proof to it. But if you wanted to, yeah, it's in the appendices. Yeah. All right. So today's lesson, that was the first part that I need to teach you, and I'm going to do some examples now. We're going to use the power rule to derive or find the derivative without doing this first principles from exercise 17A. We're skipping all of those steps to then get to this point. Now, I do want to remind you, so last session, I wrote this note down and I said I wanted you to copy that note into your exercise book, that when you find the derivative, or f dash of x, I want you to write on the side to remind yourself, this is a gradient function. Okay, what does that mean? This is a rule. What you figured out when you derive, this is a rule for any x value that you can figure out on the graph. Whatever the x coordinate is, it will tell you what the gradient is. So right now you don't know the gradient. You have no gradients at this moment. You only got a formula to find out the gradient. So as long as you know which x you want, then it'll tell you what the gradient should be. That's why I call it the gradient function. Or they usually call it the derivative function. Okay? So keeping in mind, this is just a graph or a rule of all the possible gradients you can get on any curve. That's what it is. Okay? Because that will link into the understanding when you're applying it. When they ask for instantaneous rate of change or when they're asking for a gradient function, there's a difference between the two. Okay? Let's do an example. Let's do this one now. Here we go. Example 7. You have, I'm just going to put, they didn't write f of x or y, so I'm going to write f of x. F of x is equal to x to the power of 5 minus 2 times x to the power of 3 plus 2. They want you to differentiate, essentially to find the derivative. So they want you to find f dash of x. What is this equal to? I'm going to write down the rule again, and I want you to have a go with this first, and then we'll go through the answers. So what most students, for the first time when you're first learning it, most students will get this one wrong. I'm going to teach you 2 ways of looking at it. One to use the rule, but the other one is to really understand what you're actually doing. Okay? So here we go. Here's the rule. F dash of x is equal to n times x to the power of n minus 1 if you have a power function that is x to the power of n. Okay, so you're using this rule over here. Differentiate, please. I'm going to give you, should take you probably just under a minute and a half. So let's just make it 2 minutes. I want you to differentiate this. So you've got f of x, a quintic function or polynomial, x to the power of 5 minus 2 times x to the power of 3 plus 2. If you differentiate it using the rule to your right, what will you get? Obviously, if you did it through first principles, this would take much longer. We're just doing it with a power rule.
Do you have to inverse it because it's technically 2 times x to the 0 right now? So it's 2 times 0 times x to the minus 1?
That is true. And what does that give you?
0.
Pretty good. That's one way. So what Andre just picked up there was he said 2 is essentially the same thing as right, and this is where students don't know what to do. So these ones have the x's, and it feels easier. When you don't have an x, 2 is the same thing as writing 2 times 1. But 1 can also be written as x to the power of 0. So that's what he's doing. So he's saying, all right, well, 2 is the same thing as writing 2 times x to the power of 0. Now I can differentiate that. So according to the rule, n is 0 times x to the power of 0 minus 1. That's why he's asking, do you need to do the reciprocal or inverse it? Don't forget you had a 2 here too. So that's 2 times. And then I asked him, well, what does that equal to? Well, we know 0 times anything is 0. Yes?
What's n?
N is the power. Yeah, so whatever, as soon as you see an x and it's got a power, so this is n equal to 5. This one would be n equal to 3. And this one doesn't look like it has one. Technically, n to the 0.
The power up front and reduce the power by 1.
Correct.
And then like the other way would be divide by the power and raise it by 1.
Good, that's now antiderivative.
Oh.
Yeah, yeah. Good thinking. Literally, that's what the rule's going to be like. Very good. Let's check if you've got it right. So this is what you should have got so far. If you use the rule, n is 5, so you should have 5 times x to the power of 5 minus 1. The other one is negative 2 times 3x to the power of 3 minus 1. And this one we figured out was 0. So together, this should be 5x to the power of 4 is what you should have got. And then this one should have been minus 6x to the power of 2. And that was plus 0. So together your final answer is the derivative should be 5x to the power of 4 minus 6x squared. So that's the shortcut. Instead of doing first principles, this is what you're saying. You're saying you've got a gradient function. So I'm going to write it again. This is a gradient function. It's not the gradient. It's just a gradient function. It means that you've got a rule to figure out the gradient at any point on the curve. That's what you've got here. Okay? So the skill in exercise 17B, 17C right now, it is to get you to practice to find that. That's what you're trying to do at the moment. Okay? Later on in the exercise, chapter 18, that's when you apply. So right now you're just building up your skills, your formulas, to be able to bypass the first principles and simply get straight to the derivative. That's what you're doing first. Okay? So let's have a look. Let's do another example. Let's try this one. So this one, I'm now going to introduce what you're going to do with the gradient function. Okay, so again, you've now got f of x equals to 3x cubed minus 6 times x squared plus 1. Again, I'm going to give you 2 minutes. I want you to find the derivative. What is the derivative equal to? I'm going to write down the rule again. So if you have a polynomial function, x to the power of n, then the derivative should be whatever the power is, and then minus the power by 1. Okay, so that is the rule that you've got. This is called a power rule. Have a go, because what they're asking you to do is this. But you can't do that unless you can find the derivative. And then let's unpack it. Let's try to understand what the question's really asking. I'll show you graphically so you have a visual understanding of what this question really is asking you to do. Okay? 2 minutes. 12:37. Have a go. You can do it in your head. By the end of this term or end of next term, I expect that you do it in your head. So if I asked you what's the derivative, you should be able to tell me just by looking at it. I don't want you to be sitting there writing things out, because if you are, you're really far behind. And that would mean I can almost predict if you don't get these parts here, especially when we get to chain rule, I can then predict that next year you're not getting anywhere more than 25. It's probably 25 or below if you can't do that. Because at the bare minimum,
You expect us to do it naturally without writing anything.
by the end of this year, correct. So chain rule, product rule, all of those. Product rule, I don't expect you by the end of this year, but chain rule, I'm going to make sure you do. Because next year, I know by the state average, everyone should be able to do power rule instantly. Chain rule, yes and no, but that's how I know if you're going to get a 25 rule or not. Just basically on your algebra and how much you've practiced, I can predict based on this. Here we go. All right. Time's up. Check your answers. Here we go. Same thing. Leave the 3. That's not the one we're differentiating. We're differentiating the power. So you should have got 3x to the power 3 minus 1, which is 2, minus 6. I'm going to write it again. Minus 6 times. We're differentiating the x squared. So that's times 2 to the power of x. 2 minus 1 is 1. And then similarly, with this one, this is the same thing as writing x to the power of 0. And you can then write it as plus 0 times x to the power of 0 minus 1. Here we go. You should have got 9x squared minus 12x plus 0. Yes?
It's like substituting x as 1 though, right? So it should be.
Ah, you're talking about this one here? All right, very good. Very good. So, first mark comes in this step. Second question. They're asking you to find f dash of 1, and it's very good. Ollie's shown me that he can read a function notation. Listening? Shh. Don't talk while I'm speaking, thank you. Because I'm recording. The background noise just doesn't sound good for those who are watching. So here we go. F dash of 1. So Ollie is correct. He has noticed that we've got f dash of x as a function. But when you write f dash of 1, that simply means I'm substituting wherever x is, I'm substituting 1 into the function. So if my function is 9x squared minus 12x, then the rule should give me as 9 times 1 squared minus 12 times 1. This gives me 9 minus 12, which gives me -3. Okay? Now, most of you by next year should be able to at least do that. So if I have you next year, hypothetically, if any of the teachers have you and I see your SAC mark and you can't do that, I guarantee you by the end of the year, if you still can't do that next year, you're not going to get a 25. That's just, it's just the average. Everyone will be able to do it. The ones that I've seen that couldn't do it, those are the ones that get 19, 20s as their raw scores. That's how I know. It's just because this is one of the most basic skills in derivatives. It means you're not ready.
I mean, do it all, do it in your head.
Well, one layout is how I tell, but yeah, you should be able to do it in your head too. So first thing is you should be able to do this in your head. And then if it's easy enough, yeah, you'll be able to tell what the derivative at that point is. Now, this is the next point. So the next one is, well, what does that mean? So you've done this whole step. Most students will be able to do this in the state, but why is it that they struggle with calculus? It's what this means. Okay, so most students will get this number. They'll get -3. Great. What does that mean?
Doesn't that just mean when the point of x is at 1, then the gradient's -2?
Very good. Now let's look at this visually. That's very good. So that means you've picked up on what I'm trying to say. And it's a very simple concept, isn't it? Why does the state not get it? It's not hard. It's just that if we're not spending time to understand the mathematics that we're doing, it feels like magic, right? So let's visualize what this is. I'm going to use Desmos so you can visualize what it is. And what Lohit just said is exactly what I want you to picture every time you do these kind of problems. I need you to visualize what it means. So here we go. We're going to go to Desmos. I'm just going to add up Desmos. For those who don't know, you can type Desmos graphing calculator in Google. We're going to go Desmos. Here we go. Comes up. So what equation do we have? We got f of x is equal to, whoops, not that one. It was 3x cubed minus 6x squared plus 1. So this is what our graph looks like, right? We're interested at 1. So at 1, you can already see right here on the graph, 1 should give me something like, I can't really get it. There we go. Oh, 1, -2. I don't know how to plot yet. We've got 1, -2. Okay, so I'm going to screenshot this. Let's visualize this. So this is what we have. This is our function. Here we go. This is our function. So I'm going to write down the notation and what you've been doing. So here we go. This is f of x. This is f of x. That's your function. What you figured out is that at x equals 1, so I'm going to draw here this point here, at 1, it's -2. But they didn't tell you it was -2. So in your exercises for chapter 18, you just need to figure out that y value. That's all it is. So I'm just going to put here y, even though we know it's -2. All you're doing is this. If x is 1 here, I'll probably use another color. 1, and this is -2. You've got this point on the graph. They said find the derivative. You found the derivative. This is your derivative, which you don't see right now. One of the challenges of this exercise is they will ask you to sketch the derivative graph. We won't touch that yet. But at the moment, what did you just figure out? You're right. This is the gradient. But the gradient of what? See, where does m equal to -3 exist? This exists from drawing a tangent line, so a straight line that touches this particular point when x equals 1. So I'm going to draw it. That's my tangent line. When x equals 1, so this is x. When x equals to 1 on the f of x, there's a tangent line that touches that point exactly at x equals 1. This tangent line is a straight line. Y equals mx plus c. What you figured out just now is that m is -3. That's what you're doing. So visually, this is what you have now. You now know it's y equals to -3x plus c. That's all it is. Now I'll tell you what chapter 18 is, and you don't have to get to all the way to chapter 18 to understand the theory. All they're doing now from applications is you figured out that. Chapter 18 says find the equation. Now let's think about it. I don't have this y value, but if I wanted to find this y value, knowing that this is my function, and x equals 1, how would I find the y value? We know it's -2, but But how would I prove it? How would you find the y value? What would you have to do? Yeah, because the f of x is the function. This is the function. So what I would have done is if I wanted to know this y value, that has to be when it's f of 1. That tells you the y value when x is 1. So what was our function again? It was 3 times 1 cubed minus 6 times 1 squared plus 1. This gives you now 3 minus 6 plus 1. And you can see 3 minus 6 is negative 3. Negative 3 plus 1 is negative 2. That's how you would have got the y value. But look at this. That didn't take a lot of mathematics to do. Now that you know this coordinate, I'm going to fix that and right here. This is now negative 2. My question is, how do you find this then? Because you almost got the equation. Chapter 18 gets you to find this equation. You found the derivative. You got the function. You found the derivative. You subbed in x equals 1 and you've got the gradient. Great. How do you find C now that you've got a coordinate? Yeah. You substitute in. That was year 9 mathematics. Year 9 mathematics, you're trying to find, this is all you're trying to do. You're trying to find this straight line, which I'll draw it again. This was the straight line. That's the tangent line. Y equals mx plus c. You found the equation as y equals to negative 3x plus c. But notice that tangent line, the only one point you knew was that one. That's the only point that the line crossed through. So that means when x is 1, y should be negative 2 for this equation. So in chapter 18, all they add on extra is at or when x equals to 1, y equals to negative 2. And how do we know that? We subbed it in before. Now you get negative 2 equals to negative 3 times 1 plus c. Negative 3 plus c. C must equal to 1. So that means your equation for the tangent line should be negative 3x plus 1. And if this was easy for you to understand, that's chapter 18. That's the beginning of chapter 18. This is an application question, and I promise you that right there is one of the most challenges across the state. Isn't it strange? It's a very simple idea that all you had to learn, the only one thing that was year 11 was this. Use the rule. The rest is understanding what you're doing. And that's the part that most of the students in the state don't get. They don't understand what the derivative means. So they don't know what this negative 3 means, and they stop there. But if you understood what you were doing, all you found was this. The next steps are all to do with linear equations, back into year 9 mathematics. So I'll prove it to you now. So we apparently said that that straight line should be negative 3x plus 1. So if you watch, I go back to my Desmos, and now we actually type in another equation. And I type now g of x, a different equation, and I said negative 3x plus 1. Look at where it exactly hits the graph. It's exactly at the point what we wanted. That straight line has an exact tangent right here. That was what we calculated. That's chapter 18, 18a. You can have a go with that, and it's not hard. You can do it for every single exercise you do, but it's just the theory. Theory wasn't hard to understand. What was the hardest thing? Was to understand what the derivative means. And remember, it comes from first principles. You're just moving that point so close to the one point. Once you know that gradient, that's what you've done. That's all it is. Gradient at one point, instantaneous rate of change is what this is. Beforehand, what is that? Just a gradient function. It's a gradient rule. It's a rule to find all possible gradients at any point. In your question, they happen to say at 1. But you could have found the gradient at any point. It could have been at 0, it could have been at 2, could have been negative 2 on that curve. But that's all it is. Every single point will have a different gradient. That's why you have a gradient function. That's the derivative. Instead of doing first principles, that's a shortcut. But that shortcut only works for power rules. From here onwards, it's about you playing around with the puzzle or the problem that you get.
On a start for an exam, we have to show our working out that. But I know you said you want to. Depends on the marks.
This one? Up to this point? Yeah, so up to this point, guaranteed. You don't have to do what I did over here, but there are certain questions when it talks about greater than, less than. Sometimes the best way to prove something is by a graph. It's much easier. And then, obviously, this part you have to calculate. So that's 18a. If you're doing that. We'll get to that next term, but if you understand what I'm saying already, you can technically just flip over to that and you'll be able to do it. I'm just going to teach you, beginning of next term, is all the functions. We've done today, polynomials. Next term, you're going to learn how to find the shortcut to sine, cos, tan. You find the shortcut for exponential, shortcut for log, and then combinations of that. Log of a sine, log of an x squared, square root of a sine. How do you find the derivative of all that? That's what you're building. You're building an arsenal of skills to find the derivative. That's all it is. Okay? But what you do with it afterwards is what's counting for next year. So most students struggle with knowing all the techniques to find the derivative. That's where it is. Okay?
Is term 4 like just going to be calculated?
Yep.
Just term
Oh, well, there's probability at the very, very end of term 4.
So we're doing distributions, right?
No distributions. It's just a conditional probability, that kind of idea. But I'm spending a lot of effort on calculus because I noticed the year 12s that came to me this year, they didn't know how to do chain rule or product rule. And that's something that I think you should know in year 11 because it makes your learning much easier when you get to year 12. Okay, so spend the time. Next term, I'm going to be training your derivative skills. You're going to be able to do power rule, chain rule. Ideally, you can do that in your head. So if you can look at an equation and do that in your head, that's what I want you to be able to do. So you have to be able to differentiate using chain rule. When in your head, you look at it, and you should be able to tell me what the derivative is. Okay? But we're going to stop there.